Okay, it's time to start today's session. First speaker is Professor Miho Murata at Shizuoka University. Title of her talk is Global Well-posedness for a Q-tensor model of nematic liquid crystals. So, please.
Thank you for introduction. Can you hear me? Okay.
Okay.
Okay, thank you. So first of all, I'd like to thank the organizer giving me a chance in this conference. So in this talk, we consider global well-posedness for a Q-tensor model of nematic liquid crystals. My talk is based on joint work with Professor Yoshiro Shibata at Waseda University. So before I explain our equation, I introduce some history for Q-tensor model. The Q-tensor was introduced by the Gen in 1974 in order to characterize orientation and degree of ordering for the liquid crystal molecules. In his theory, Q is known as a traceless and symmetric matrix, and this N is space dimension. And based on his idea, Bayes and Edwards in 1994 proposed the model for viscous incompressed liquid crystal flow, which is a coupled system by the Navier-Stokes equations with a parabolic type equation describing the evolution of Q-tensor. So more precisely, so this is Bayes-Edwards model. So we call BE. So in this talk, we consider this problem in whole space. And U is fluid velocity, P is pressure, and Q is order parameter of liquid crystal molecules. So this div is divergence for matrix given by this form. And the first equation is Navier-Stokes equation with additional stress tensor tau and sigma, which means the evolution of flow is influenced by the liquid crystal molecules. And tau and sigma are defined by this equation. Eta is a scalar parameter, and h is given by this equation. And from modeling point of view, we assume L and C are positive constant. For simplicity, we set L equal to 1. For mathematical point of view, we also assume A is positive constant. And by this definition, for tau and sigma, the linear term appears in only H, and the linear term of H is Laplace Q minus AQ. Therefore, the linear term of the first equation is Stokes equation, and from here, divergence Laplace Q minus AQ. And for the second equation is evolution of Q-tensor, and this S nabla UQ is given by this equation, and this du and wu are symmetric and unsymmetric part of nabla U. So S nabla U and Q denote the described how to say how to gradient flow stretches and rotating Q-tensor. The linear term of S nabla UQ is eta times du over n. Therefore, the second term has a linear term. The left-hand side, dtq minus 2 eta over n du. And from right-hand side, we also have Laplace Q minus AQ plus nonlinear term. And for this problem, so concerning the existence of solution, there are many results recent year. So concerning weak solution, Peck and Zarnesk, 2011 and 2012, they consider the problem in the case eta equal to 0 or eta is sufficiently small. They prove the existence of global weak solution in whole space, dimension n equal to 2 or 3. And they also show the weak strong uniqueness in whole space. And Anna improved their result. Anna only considered the case eta equal to 0 and the existence of global weak solution and uniqueness in whole space for lower regularity initial data. And for ending in 2015, they also considered the model in eta equal to 0, and then they show the existence of a global weak solution with a more general energy functional in whole space. So there are many results, but almost all results in eta equal to 0 or sufficiently small eta. So this scalar parameter eta denotes the ratio between the tumbling and aligning effect that the shear flow exert over the directors. Especially eta equal to 0 means that the molecules only tumble in a shear flow but not align. So on the other hand, concerning strong solution, Abel-Stoltzmann-Liu in 2014, they proved local well-posedness and the existence of a global weak solution with higher regularity in time in the case of inhomogeneous mixed Dirichlet-Neumann boundary condition in bounded domain. They consider the problem for any eta. And Liu and Wang improved Abel's result. So they showed local well-posedness to the case of isotropic elastic energy, and they improved the spatial regularity of solution. And Abel-Stoltzmann-Liu also showed the local well-posedness with Dirichlet boundary condition for the classical Bayes-Edwards models, which means the fluid viscosity depends on the Q-tensor. And same time, Cavatella proved the global well-posedness in the two-dimensional periodic case for any eta. After that, Shao proved the global well-posedness in a bounded domain. So he constructed a solution in maximal LPLQ regularity class. So, but he only considered the case eta equal to 0. And I especially referred Professor Schombeck and Professor Shibata's result. So they prove global well-posedness in whole space in the maximal LPLQ regularity for any eta. So I explain what is difference between our problem and their problem. So this is our problem. So in our problem, equation of U and Q are completely coupled by this blue part, including third order derivative of Q-tensor. In this, this beta is defined to eta over n. On the other hand, they consider the system removed this blue part from the first equation. So therefore, the linear part of the first equation is Stokes equation. And so linearized equation for U and Q are essentially separated. So the first they showed they solved Stokes equation, and then they solved shifted heat equation given du. So therefore, the problem is a little bit different. And our goal is the following. For some eta, so we also need some restriction for eta, but not so small. And we prove global well-posedness for small initial data in the maximal LP-LQ regularity class. So for our problem, maximal regularity class means velocity u belongs to LP in time, W2Q in space, and W1P in time, LQ in space. And Q-tensor belongs to LP in time, W3Q in space, and W1P in time, W1Q in space. So before I explain the main theorem, I introduce notation. S0 is traceless and symmetric matrix space. And for Q-tensor, Sobolev space is given by this form, XRN S0. So for example, LQRN S0 means LQ norm for each component is bounded. And JQ is solenoidal space. And DQP is space for initial data. So velocity part belongs to this Bezos space and divergence-free space, and Q-tensor belongs to this Bezos space. So this Bezos space equivalent to the time trace space of maximal regularity space. And XPQT is the space for solution, and U and Q belong to maximal regularity space. And for simplicity, we set norm of WMLQ. This means WMQ norm for vector plus WLQ norm for matrix. I sometimes omit Rn like this. And we also define NUQT is the following. And this B is decay rate. So we decide later. And this bracket T equal to 1 plus T square and 1/2. And we take exponent for space Q1 and Q2. So we need 2 exponent. And for Q1, and we can get decay estimate for only derivative term. And Q2 is greater than Q1, therefore we get decay estimate in W23Q2. And this is our main theorem, so theorem 1. The dimension n is greater than or equal to 3, and eta, absolute value eta is less than n over half, and sigma is sufficiently small, and P and Q1 are close to 2. And we set Q2 is sufficiently larger than dimension n. And Q1 is essentially needed for decay estimate, and Q2 is essentially needed for maximal regularity. Moreover, so this constant sigma is essentially for Q1 because from point of view of maximal regularity, we don't have L1 estimate. So, but we consider LQ1 half estimate. So, if Q1 half, we consider Q1 half. So, we need plus sigma. And decay rate B equal to n over 2 times 2 plus sigma. Then sufficiently small epsilon. So there exists epsilon such that for any initial data belong to Bezos space and W01 Q1 half with smallness condition, and the BE has a unique solution belong to maximal regularity class and satisfying decay estimate. So in order to get global well-posedness in unbounded domain, we showed maximal regularity estimate and LPLQ decay estimate for semi-group. In order to get maximal regularity estimate and generation of semi-group, we use R-boundedness. So this strategy is the same as Professor Kubo's talk. So the first, I introduce definition of R-boundedness. So X and Y are Banach space, and the family of operator T is called R-bounded on bounded linear operator from X to Y if there exists constant C and P such that for any natural number N, Tj, Fj, and sequence Rj of independent symmetric -1 or 1 valued random variables, we have the following inequality. The smallest such C is called R bound of T, which is denote this notation. So we don't use this definition directly, but hereafter we use this notation. So the important thing is the following remark. So setting n equal to 1 in this definition, we see that R-boundedness implies uniform boundedness of the operator family T. So this means if we get R-boundedness, we can automatically get resolvent estimate, and then we get generation of analytic semi-group. So we try to get R-boundedness solution operator. So first we calculate solution formula by formal calculations. So this is a resolvent problem corresponding to our problem, and beta equal to eta over n. And first, taking divergence of the first equation of resolvent problem, this part, and we get the pressure term is given by Q-tensor and right member F. And inserting this equation into the first equation of resolvent problem, we can eliminate pressure term, and we get the second equation. Moreover, the second equation of resolvent problem equivalent to this form. So thanks to this form, if we get the solution formula of velocity part, we can immediately get the solution formula Q-tensor part. So in this talk, we only consider the solution formula velocity part. And applying this operator to the second equation, we get so we can eliminate Q-tensor part. So for example, if we applied this operator to this red part, so now we have the divergence-free condition. Therefore, the div du equal to Laplace u. So therefore, we get this Laplace square minus Laplace u. And we also have the right member. And for blue part, we use divergence-free condition again. We can cancel velocity part u. We remain, so remaining part is only right members. And we set operator of left-hand side P lambda. And then we get a solution formula for velocity part. Like this. Now, applying Fourier transform and Fourier inverse transform, we get the solution formula like this. And this peak C lambda is given by the Fourier transform of P lambda. So in order to get R boundedness, one of the important point is how to choose set of resolvent parameter lambda. So we call the sector. So next slide. For this purpose, we first analyze peak C lambda. And peak C lambda is given by this equation. Then we divide low frequency part and high frequency part. And we analyze root of peak C lambda. So for low frequency part, if we assume 1 minus beta square is positive, and also we assumed A is positive constant, and then the roots appear the negative part of real axis. Therefore, we can expect global well-posedness. And for high frequency part, so see, sorry, I forgot. So by the condition 1 minus beta square is positive, we can get eta is less than n over 2 because beta equal to eta over n. So therefore, we need this condition to get main theorem. And then we consider the high frequency part, lambda plus and lambda minus appear here. And then we choose sigma 0 is this angle. And then we fix sigma from sigma 0 to pi half, like this. Moreover, we choose lambda 0 is sufficiently large. And then this part is sigma lambda 0. So we choose this sector. And we choose lambda belong to this sector. And then we show the R boundedness. So to get the R boundedness, we use the following useful lemma proved by Denk, Schoenabelt, and Enomoto Shibata and Saito. And Q is 1 and infinity. And operator K lambda and L lambda are defined by Fourier transform, Fourier inverse transform, like this. And this K C lambda and L C lambda satisfy this estimate for any sigma and multi-index alpha. And then we get R boundedness solution operator K lambda from LQ to LQ, and L lambda is from W1Q and LQ. So by this estimate, so absolute value of LC lambda is less than C power 1 minus alpha. So compare with KXC lambda, we have additional XC. So this XC corresponding to the derivative. Therefore, L lambda is R-bounded operator from W1Q to LQ. So we use this lemma. And we check this estimate for our solution formula. So this is our solution formula. And to use the previous lemma, we should consider the estimate of peak C lambda. And first, we consider this lemma. And this sigma 0 is same as angle before, same angle before. Then for any sigma and C lambda, and we get this estimate. We check this lemma. And if beta equals to 0, we can cancel this term. So we use the following well-known lemma. So immediately we get this estimate. So next we consider beta does not equal to 0 case. And recalling peak C lambda satisfy this expansion. For low frequency part, we can prove by the same way as beta equal to 0 case. For high frequency part, we can get lemma by direct calculation. In fact, lambda is given by this form. And then we can write lambda plus minus like this. And then we calculate absolute value of lambda minus lambda plus minus square. So of course we can get the first equation. And then lambda times lambda bar equal to first term, and lambda plus minus times lambda plus minus bar equal to second term. And noting that lambda plus minus bar equal to lambda minus plus, therefore lambda times lambda plus minus bar and lambda plus minus times lambda bar equal to essentially this third term. Now we use cosine theta minus plus sigma 0 is greater than or equal to minus cosine sigma minus sigma 0. So this is given by the condition theta. And if we use this inequality, we can eliminate theta, and then we get lemma for high frequency part. So now we get this estimate. By this estimate and Bell's formula, we see that derivative peak C lambda inverse satisfies this estimate. So this n equal to 0 or 1. So using this estimate, we can show the R-boundedness for velocity part. So we only consider these 4 terms. So if we consider nabla square u, we have additional c square. Therefore, so roughly speaking, so this from this term appears c to 4th power, and peak C lambda also has c to 4th power. And then we have this inequality. The second term is same as the first term. And the last term, if lambda is sufficiently large, we get same estimate. And this red part, we see that this estimate. Therefore, by using a useful lemma, we can get R-boundedness. So now we consider only nabla square u, but by the same way, we can estimate for lambda half nabla and lambda. So for Q-tensor part, we also get R-boundedness by the same way. So summing up, we get Theorem 2 concerning R-boundedness. Q is 1 infinity, and then sigma, for any sigma, there exists sufficiently large lambda 0 and operators A lambda and B lambda, operator valued holomorphic function defined on sector. And then this A lambda, B lambda solution operator for velocity part and Q-tensor part. Moreover, we get R-boundedness for S lambda, A lambda. This means nabla square U and lambda half nabla U and lambda U. And also we get T lambda, B lambda R-boundedness. So T lambda Q is corresponding to nabla cube Q, lambda 1/2 nabla square Q, and lambda Q. So this part belongs to LQ, and lambda Q belongs to W1Q. Therefore, this operator family T lambda B lambda is R-bounded from W01Q to LQ cross W1Q. So using this theorem, we get generation of analytic semi-group and maximal regularity estimate. The first we consider the generation of analytic semi-group. So we consider the linearized problem, right member equal to 0. And we set xq equal to jq cross w1q. And linear operator define this form, and this P denotes solenoidal projection, and domain A is W2Q and JQ cross W3Q. As I told you, R-boundedness implies usual boundedness. Therefore, by R-boundedness, we get this resolvent estimate. Then we see that operator A generates continuous analytic semi-group on XQ. By this fact, we get the standard estimate for semi-group for if time t is small. So this estimate is one of the important estimate in this talk. And next, we consider the maximal LP-LQ regularity estimate, and combining R-boundedness and the following operator-valued Fourier multiplier theorem proved by Weiss 2001, we can get maximal LP-LQ regularity estimate. So important point is if we define operator Tm is this form, Fourier transform and Fourier inverse transform, and this M satisfied R-boundedness, and also tau times derivative M also R-boundedness, and then we get the Tm phi. So this operator is extended to bounded linear operator from LPx into LPy. Moreover, we get this estimate. So if x and y are sovereign space in LQ framework, we get LP-LQ maximal regularity estimate. So we checked, we can apply this theorem for our problem. So we consider the linearized problem. So in this time, initial data equal to 0. And this U equal to velocity and Q-tensor, and right member F and equal to PF. So this P is solenoidal projection and G. And we assume exponential minus gamma 1 TF belong to LPW01Q. So this gamma 1 is sufficiently larger than lambda 0. So now we set this sector, and here is lambda 0, and we set gamma 1. And we consider the maximal regularity estimate in this region. The first, F0 is the zero extension of F to time t is negative. We consider this linearized problem for whole time. In applying Laplace transformation, we get the resolvent problem. We already get the existence of a solution for resolvent problem, and the operator family are R-boundedness. And A lambda, B lambda are bounded. And by Laplace inverse transform, we can define U1. So this solution is given by Laplace inverse transform, because Laplace F0 is holomorphic if gamma is sufficiently large. So gamma is greater than or equal to gamma 1. This Laplace F0 is holomorphic. Therefore, we can define U1 as follows. And by using Laplace relation for Laplace transform and Fourier transform, we can write U1 by Fourier transform. And for this formula, we can apply the operator valued Fourier multiplier theorem, and then we get maximal LPLQ regularity estimate. But we only get the exponential growth type maximal regularity estimate. Therefore, we can not get the global well-posedness only this estimate. So we also need LPLQ decay estimate. So we don't not so much time. So I only explain the result for LPLQ decay estimate. So we consider this linearized problem, right member equal to 0. So the generation of analytic semi-group implies that the solution given by the following integration. So this gamma is, so here is sigma, and this gamma is this integral path. And then we divide low frequency part and the high frequency part. We change the integral path, and then for the low frequency part, we use a decay estimate for heat kernel, and then we get this decay rate. And for high frequency part, by the Fourier multiplier theorem, we get exponential decay estimate. Combining these two estimates, we get the LPLQ decay estimate for semi-group if time t is large. And summing up, we get the maximal regularity estimate and the LPLQ decay estimate, and we also get a standard estimate for semi-group. So combining these three estimates, we can consider the nonlinear problem. So on Tuesday, Professor Shibata explained how to solve the quadrilinear parabolic equation or quadrilinear hyperbolic parabolic equation. So we can apply the same method to our Q-tensor problem. So we check the method. And we use Banach fixed point argument underlying space IT epsilon. And given UQ belong to this underlying space, V and P are solution to the following equation. So in order to prove V and P also belong to this underlying space, today we only checked NVP. So this norm is less than C epsilon square. So for this purpose, we divide the equation into two parts. The first part is time-shifted equation, and the second part is compensation equation. So V1 and P1 satisfy time-shifted equation. So time-shifted means that we add lambda 1V and lambda 1P. And we use maximal regularity estimate for this time-shifted equation. And V2, P2 satisfy compensation equation. And for this equation, we use decay estimate and standard estimate for semi-group. First, we consider shifted equation, time-shifted equation. So we consider the corresponding to time-shifted, we consider the linearized problem corresponding to the time-shifted equation. And we get the maximal regularity estimate without exponential weight. So because, so we take lambda 1 is sufficiently large such that lambda plus lambda 1 belong to sector. For lambda belong to imaginary axis. Therefore, we get a maximal regularity estimate without exponential weight. So roughly speaking, if we don't add lambda 1V and lambda 1P, we can get maximal regularity estimate only this area. But if we consider time-shifted equation, we can shift this line to imaginary axis. So therefore, we get the maximal regularity estimate like this. And this theorem says that V1 and P1, so decay rate of V1 and P1 is same as right member FNG. So this combining this estimate and estimate for nonlinear term in LQ1, LQ2, and we also need LQ1 half estimate for compensation equation. So combining these two estimates, we get this decay estimate for V1 and P1. So we need condition Q2 is greater than N because we use Sobolev embedding property. And we also need 1 minus BP is negative because of integral convergence. And next, we consider the compensation equation. So this A is the same linear operator. And the compensation equation equivalent to the following equation. By Duhamel principle, we can write solution as follows. And we only consider the second term. In the case time t is greater than 2. So we especially consider the estimate of special derivatives for this second term. We divide 3 parts. In 0 to t minus 1, we use LPLQ decay estimate with P and Q equal to Q1, Q1 half, or Q2, Q1 half estimate. And for time t minus 1 to t, we have singularity if time t equal to s. So we use standard estimate for semi-group. So thanks to this estimate, decay rate of V2 and P2 is the same as V1 and P1. Therefore, the decay rate of nonlinear problem is decided from this estimate. Now, combining these two estimates, the derivative term is estimated by V1 and P1. So we already get the estimate for V1 and P1. Therefore, we get the derivative V2 and P2 is less than NUQ square. But we get only J equal to 1 or 2 if Q equal to Q1 case. So because LQ1 half estimate, decay rate of semi-group equal to this one. And now we choose Q1 equal to 2 plus sigma. Therefore, decay rate of semi-group equal to same as B. Therefore, integral convergence does not hold. Therefore, we choose only J equal to 1 or 2. So combining estimates for time-shifted equation and estimate for compensation equation, we have decay estimate. So this epsilon is independent of time t. Therefore, we get global well-posedness. So that's all. Thank you for your attention.
Thank you very much for interesting talk. Are there any question, comment? Question or comment? No question? Okay. So I have one question.
Yes.
You consider the whole space case.
Yes.
How about the domain with boundary? How, for example, half space or bounded domain case or and so on.
So now we try to the half space case, and by partial Fourier transform, we get a solution formula, and now we consider the estimate for Lobachevsky determinant. And if we get this estimate, I hope we get the half space case, and then localized technique, we get another space.
Okay, thank you very much. Okay, Prof. Watanabe, please.
Thank you for your interesting talk.
Thank you.
And as far as I understood, you will have some hyperbolic effect due to the low frequency part.
Yeah.
Is it possible to derive some hyperbolic effect, for example, some diffusion wave property or something like that, in order to describe the hyperbolic effect of the solutions? As far as I see the decay estimate, it's quite similar to the decay estimate as Professor Shibata explained it on Tuesdays.
Yeah.
Okay.
Sorry. I will consider it. Sorry.
Okay. Thank you so much.
Okay. Okay. Are there any other question? Go ahead. Okay. So if not the case, thanks speaker again.
Thank you very much.